So now we move to simple image features. So like we said earlier, light reflects of objects in the scene to form an image consisting of, say, 12 million 3-byte pixels. As with all sensors, there will be noise in the image, and in any case, there's a lot of data to deal with. So the way to get started analyzing this data is to produce a simplified representation that identify what's important in all this data. Okay, even without focusing on the detail at first. So most of the neural networks that we will learn about essentially learn these representations from data. So start by identifying these simple features. But there are 4 properties of images and videos that are particularly general. So edges, texture, optical flow, and segmentations into different regions. So let's start with edges. So an edge occurs when there is a big difference in pixel intensity across part of an image. Building representations of edges involves local operations on an image. It doesn't require any knowledge about what's in the image. So you're just trying to identify places where the pixel intensity goes from very high to very low or very low to very high. And then that gives you a clue that this might be an edge, even if you have no idea what the image is representing. So edge detection then comes very early in the pipeline of operations. Okay, when we are training neural networks, you will see that in the very first layers, that's what takes place. Okay, we try to identify these edges. So edges in the scene very often result in large changes in image intensity producing edges. For example, depth discontinuities can cause edges. The surface normal changes, surface reflectance, shadow also can cause an edge. Okay, so because in that case, remember, all we're looking for is a change in intensity between 2 adjacent pixels. So then finding edges requires carefully looking at the intensity difference, because if we just focus on intensity difference, this can give us mistakes in identifying edges due to noise. And we define noise as the changes to the value of a pixel that don't have to do with an edge. So for whatever reason, if there's a change in the intensity of a given pixel that's not related to an edge at that pixel, then we call that noise in that case. So here we can see 3 different types of edges. You have 1, depth discontinuities. 2, you have surface orientation that changes between the top surface and the side surface. On 3, you have reflectance discontinuity. You can see the angles are different, right, facing the light. And on edge 4, you have illumination discontinuities. You have a shadow, right? You can see that the illumination is different. So in order to deal with noise, we apply smoothing, which involves using surrounding pixels to eliminate that noise. So what we do is we predict the value of a pixel as a weighted sum of nearby pixels. Okay, so and the closer that nearby pixel is to the pixel I'm interested in, the higher the weight I give it. Okay, and then I can apply a Gaussian filter, which is the convolution of 2 functions, f and g, And that's where the name convolution neural network comes from, because we're applying these filters over and over again. So this convolution operation, we give it this symbol h equal f star g. We apply that over all pixels of the intensity function at any point x and y times the Gaussian at distance d, where d is the distance from the point where we're smoothing around. Okay, so it depends on how far the point is from x naught, y naught. So you can see the convolution operation in one dimensional is a summation from negative infinity to infinity, f of u times g of x minus u. And then in 2D, in that case, we just replace the single summation with double summation. And the function becomes a function of 2D variables u and v, and then the Gaussian is a Gaussian of x minus u and y minus v as well. So this chart right here shows you that smoothing process. So at the top you have the intensity profile I of x along a one-dimensional section across a step edge. Okay. The middle graph shows the derivative of the intensity I prime of x. So you can see in the middle there, this is the highest derivative, which corresponds to that big jump in intensity that happens right here. So, and here, of course, the intensity drops to zero. So, and that's why you have that very big negative derivative right there as well. So large values of that middle graph there correspond to edges. So we can conclude that probably there's an edge at 50 and another edge at 100. But you can see the function is noisy. It's not very clear. Okay. Now, if we smooth that derivative, the middle chart, we obtain that bottom chart, which is the smoothed version of the intensity after applying the convolution process that we described earlier. In that case, you can see that at 75, it seems that there's a big derivative, right? It seems that the derivative is high here, but in reality, there's no true edge here. So it was smoothed out. You can see that in the bottom chart, this spike here at 75 does no longer exist. And then we conclude that the only real edges are at 50 and 100, and there's no edge at 75. Okay, after applying the smoothing process. So here's for example, another explanation of this. So on the left we have a photograph of a stapler, and then on the right we have the edges that we can compute based on that pixel intensity from this photograph. Now the output is not perfect. Okay, there are gaps where no edges appear, and there are noise edges that do not correspond to anything of significance. Try to find them when looking at this image in your textbook. So, but this, again, this is the very first step in image processing, right? We're going to have a lot more layers coming after that. So later stages of our neural network will have to correct for these errors. But as a first step, that's not bad. Okay, we already can tell that this is a photo of a stapler. Now, in addition to edges, we want to detect textures in a given image. So texture refers to a pattern on a surface that we can sense visually without touching. So usual rough model of texture is a repetitive pattern of elements. Sometimes we call them pixels. It's a property of an image patch rather than a pixel in isolation. So it's a property of a group of pixels that together they make up a patch of an image. So no change when the lighting changes, which is true, right? The texture should not change. Change in a sensible way when the patch rotates, and it's useful for identifying objects and matching patches. So basic construction of a texture representation. How do we identify textures then? We compute the gradient orientation at each pixel in the patch, and then characterize the patch by a histogram of orientation. Okay, so in that case, we don't really look at intensity or change in intensity. We're looking at the orientation. Okay, the gradient of the orientation of the gradient. The next thing we want to detect is what's called optical flow. So optical flow is defined as apparent motion whenever there is a relative movement between the camera and one or more objects in the scene. So it describes the direction and speed of motion of features in the image as a result of relative motion between the viewer and the scene. So it's a measure of similarity, sum of square differences. So in this equation, we have x and y is the range of pixels in the block centered at x0, y0. And we find dx, dy that minimizes SSD, the sum of square differences. And then the optical flow then at the point x0, y0 is then, we call it dx, dy, which is defined by the derivative of x over time and derivative of y over time as well. Okay, so this requires some textures in the scene to be able to tell in what direction the image is moving. So there's optical flow. So this results in windows containing a significant variation in brightness among the pixels. So here's an example of this optical flow. So you have two frames of a video sequence of someone playing tennis here. And you can see the optical flow corresponding to the displacement from one frame to the next. So you can note how the movement of the tennis racket is going down to the right. The movement of the front leg is to the left, right? And you can see that almost nothing else moves in this picture, right? So the right leg is not moving because you don't see the arrows are very small there, and there's no other movement we can detect here, other than maybe the upper body is going down to the right as well. So this flow right here tells us essentially in which way the different parts of the image are moving at a given point in time. Finally, what we want to do is segmentation of natural images, okay, which is essentially, it's a process of splitting the image into groups of similar pixels, okay? So what we're trying to do really is to try to detect the boundaries, okay, or the groups of pixels that make up a region, okay? So it's a classification problem. We have a boundary curve at pixel location x and y, an orientation theta, an image neighborhood center that x and y looks roughly like a disk cut into two halves by diameter oriented at theta. So what we want to do is calculate the probability that there's a boundary curve at that pixel along that orientation by comparing features in the two halves. So to train a machine learning classifier using a data set of natural images in which humans have marked the ground truth boundaries. Okay, so we have our training set will be developed by humans with boundaries that are clear, and we're trying to train the network to identify these boundaries. So the goal of the classifier then is to mark exactly the boundaries that the human marked, and no additional boundaries should be marked in there. Okay, so that's how we will train a classifier to identify segments in a natural image.